Just 8 years after the founding of the United States, a French inventor attached a primitive hand-cranked propeller to a manned balloon. This is the first recorded means of aerial propulsion. Propellers were seen by early aviation pioneers as giant fans beating the air to move aircraft forward, until the Wright brothers pioneered the twisted airfoil of the modern propeller. Using data from their wind tunnel, they developed a spinning wing that provided substantially more force than previous propeller technology. This force is called thrust, and it overcomes the friction or drag of air on the aircraft, allowing it to move forward through the skies. Lift, generated by the aircraft's wings, counteracts gravity, ensuring the aircraft remains aloft. The Wright brothers' propeller designs were so efficient that even today's advanced propellers are only 8% more effective at providing thrust. With propellers reaching mature designs early in the century, aircraft designers knew that in order to fly faster, they needed to spin larger and larger propellers at higher and higher revolutions. The Propeller Research and Test Laboratory at Wright Field could test propellers up to 45 feet in diameter at speeds up to 4,500 revolutions per minute. This lab tested all propellers accepted for use by the U.S. Army Air Corps and the U.S. Navy. In May of 1917, 1 month after the United States declared war on Germany, the U.S. War Department commissioned a design of an aircraft engine that would rival the world's best engines. By 1919, over 20,000 of these motors, known as Liberty engines, had been produced. This singular motor kick-started a whirlwind of U.S. military aircraft engine development. In 1918, on the 14,000-foot apex of Pikes Peak, the U.S. Army Air Service and its contracting partner General Electric demonstrated a turbine attached to a 350-horsepower Liberty aircraft engine. This supercharger used the engine's exhaust gases to drive a turbine that compressed incoming air. This boosted horsepower at higher altitudes, allowing planes to reach into the stratosphere without losing power. Further Air Force turbine research helped develop reliable superchargers that allowed the Allied forces to achieve strategic superiority during World War II. World War II saw the limits of piston-engine propeller-driven aircraft. Even with extreme streamlining, supercharged engines, and very efficient propellers, aircraft of the Second World War rarely exceeded a speed of 450 miles per hour. Leaping from pistons to turbines, Frank Whittle's work at the beginning of World War II started the jet age. Jet engines work by ingesting air in the front of the engine, then compressing this air by sending it through a series of spinning turbines, mixing it with fuel and igniting it. The result is vast quantities of rapidly expanding gases moving out of the back of the engine, producing the thrust necessary to propel an aircraft forward. In October 1942, at Muroc Dry Lake, California, 2 GE engines powered the historic first flight of a Bell XP-59A Aerocomet. The jet engine development continues today and is reliant upon AFRL research to provide advances in materials, turbine blade technology, alternative fuels, maintenance and durability technology, and engine optimization. The Air Force is also heavily involved in the development of solid and liquid-fueled rocket engines. In a liquid-fueled engine, propellant and oxidizers are fed from their respective tanks into a combustion chamber and ignited. The resulting hot expanding gases are sent out the engine's nozzle, pushing the rocket in the opposite direction. A solid fuel rocket engine combines the oxidizer and fuel into a solid, and upon ignition, it burns rapidly, producing a stream of hot expanding gases. Air Force scientific research and development has vastly contributed to the rocket engines that have been used in ballistic missiles, space access for manned spaceflight and satellite launches, and other missile systems. Prior to the development of Project Apollo by NASA, the Air Force worked on the development and testing of the F-1 rocket engine used to power the Saturn V that took men to the moon. AFRL's testing facilities located on the western edge of the Mojave Desert in California, are frequently used for testing new rocket engines. Air Force scientists and engineers have guided the country's missile and space launch programs into maturity, and AFRL is looking to the future of space travel by investigating technology such as scramjet engines, hydrocarbon fuels, and electric propulsion. AFRL continues to research and develop the technologies the Air Force needs to go higher, faster to the skies and beyond.